Welcome back to the session, and today's discussion topic we have lattices and Boolean algebra. So what is all about this lattice and Boolean algebra? Lattices we'll be coming across in all networkings. We'll have it in theory of computation, those are undergoing the course. And Boolean algebra mainly it is used everywhere, right? Like in digital electronics, you can find Boolean algebra while drawing the circuits, and get or get while finding it, you will get a Boolean algebra or Boolean expression. And also in image processing, you can see this Boolean algebra. So this is a very important topic in discrete mathematics also. So because it is an application to oriented one, we will be coming across everywhere in today's life of computer world, right? So now let us see what is lattices and Boolean algebra as far as mathematics is concerned, right? So before we enter into this lattices, we should know what is a partially ordered set. So already I have told you this partially ordered set means a relation which satisfies which satisfies reflexive, antisymmetric and transitive, right? Any relation, any binary relation which satisfies, right, partially ordered set, we call it to be a pose set. Any relation R which satisfies reflexive, antisymmetric and transitive. So this it is called as a partially ordered set. Now what is this? I'll just have a quick review of all these things. So suppose if I have A to be as any element, and if each and every element, right, each and every element is related to itself, then it is said to be a reflexive. So here if I have two elements, then this antisymmetric property says that if A is related to B and B is related to A, then we will have A is equal to B, right? And this transitivity is if A is related to B, B is related to C, will imply A related to C. So this, whenever any binary relation which satisfies these properties, it is said to be a partially ordered set. So why we are talking about this partially ordered set here in lattices? So to define a lattice, first of all the set should be a partially ordered set, right? So for that only I have given you these 3 points to remember the partially ordered set. Even before going into what is a lattice, we should know what is an upper bound, lower bound, and least upper bound, greatest lower bound and so on. So this we might have done in schooling. So lower bound, the literal meaning is we may have various bounds, of which I'll have to find out what is the lower of it, upper of it, and among all the lower bounds what is the least element, and among all the upper bounds what is the lowest element I'll have to find. So lower bound, how do we define, right? So lower bound, how do we define it? Suppose I have a partially ordered set P comma less than or equal to, right? This P is a pose set, and less than or equal to, here it doesn't mean that the element should be less than or equal to, but then we have a relation. That relation may be anything else, but for our convenience sake I have taken to be as less than or equal to. I say that repeatedly, this less than or equal to doesn't mean that one element should be less than the other one. It does not reflect that way. It says that some relation will be for their set P. P is a partially ordered set. Now lower bound. So now let me take two elements A and B in the pose set. So partially ordered set. Now how do I find out whether I'll have the lower bound of this set or not? So if I want to have the lower bound of that set, this says that the element, suppose in case if I take L to be the lower bound, that element should be less than or equal to A, as well as it should be less than or equal to B. Then here L is said to be the lower bound, right? Understood? So whatever element I have in the partially ordered set, if I have L to be the minimum of these two elements when compared, then it is said to be the lower bound. And next is upper bound. So to define upper bound, let me take a partially ordered set with the relation as less than or equal to, and let us take two elements of the set A and B. So now how do I define my upper bound? So upper bound here I will have, that is, U will be greater than or equal to A and U will be greater than or equal to B. So any element, if that is greater than or equal to the element in that set, then this U is said to be an upper bound. This is how we will be finding out we will be defining a lower bound and the upper bound. And next is least upper bound, LUB. So least upper bound in the sense, I may have many upper bounds of which I have to find out which is least among them, right? So which means that I may have many elements, that is minimum of, I may have many upper bounds, like say for example U1, U2, U3, and I will have to find out what is the minimum of all these three. So minimum of all these things will be my least upper bound. And greatest lower bound, I may have many lower bounds of which I will have to find out which is the greatest. So which means that maximum of L1, L2, L3 if I have. So I will have to find out what is the greatest among all these lower bounds, and that will be the greatest lower bound. So now after knowing what is a lower bound, upper bound, least upper bound and greatest lower bound, let me define you what is a lattice. So lattice, first of all, it has to be a partially ordered set, right? Let me take the set P of P less than or equal to. This set is said to be a lattice L comma less than or equal to if every pair of elements, right? That is very, very important. If every pair of elements, in the set has least upper bound and greatest lower bound. So if each and every pair of elements in that set has the least upper bound and the greatest lower bound, then it is said to be a lattice. Suppose, say for example, in that I have, right, I have two elements A, B, right. So let this have 0 and this to be as 1. See here, I have two elements A, B. So this pair should have a least upper bound as well as it should have a greatest lower bound. Then only it is said to be a lattice. Let me check out what is the GLB of A and B. So GLB of A and B is 0. And what is A or B? That is the least upper bound. So that is equal to 1. So it satisfies the condition. So therefore I call it to be as a lattice. Understood? So a lattice is nothing else but each and every pair of element in that particular set, if it has a least upper bound and the greatest lower bound, then it is said to be a lattice. And next is we have Hasse diagram. So Hasse diagram, how to go with this diagram, or how do we draw this diagram? So 4 points we will have to keep in mind. That is, if any element is related to itself, then we need not have an arrow mark. There is a link, so therefore we need not have an arrow mark. While drawing the Hasse diagram, we should keep all this in mind. And suppose if I have an element, right, I have an element B which is above A, right, which is above A. So which means that it says that the element A is related to B, so therefore I need not have an arrow mark for it. And also if I have an element C above the sequence of the elements, right, so C is just above this, then it says that A is related to C, so I need not have an arrow mark. So these are the things we will have to keep in mind when we draw a Hasse diagram. Okay, now I will just see an example, right. I have the set A is equal to 1, 2, 3, 4, right? And I define the relation capital R to be as less than or equal to. Now I am asking you to draw a Hasse diagram for this. How do I draw it? First of all, I will have to find out what is my relation here. So relation, already I have defined it. It is nothing else but an ordered pair. The first member of the ordered pair should be less than or equal to the second member of the ordered pair. So now likewise I can have 1 comma 1, 1 comma 2, first element is less than, 1 comma 3, 1 comma 4, right? 2 comma 1 I cannot have, since because that element will be greater. So I can have 2 comma 2, I can have 2 comma 3, I can have 2 comma 4, right? And next is I can have 3 comma 1, I cannot have 3 comma 2, I cannot have 3 comma 3, I can have 3 comma 4, I can have. Then finally I can have 4 comma 4. This is what the relation, and for this relation I am supposed to draw the Hasse diagram. So how do we draw the Hasse diagram is that I have 4 elements, mark those 4 elements, right? 1, 2, 3, 4, right? How do we draw it? Each and every element is related to itself. See here, 1 comma 1, 2 comma 2, 3 comma 3, 4. I need not have an arrow mark for all this. It is understood default. 1 comma 2. So 1 is related to 2. I need not have an arrow mark for it. 1 is related to 3. 1 is related to 4. Right? 2 is related to 3. Yes, I have. 2 is related to 4. Yes, I have. Then 3 is related to 4. Yes, I have. So this is what the Hasse diagram says, right? So when I draw a Hasse diagram, I will have to have a relation. For that relation, I will have to draw the diagram. Say again, I'll give another example, right? So the set A is equal to ABC, right? The set A is equal to ABC, and the relation R here is subset, right? Now I am asking you to draw a Hasse diagram for the power set A, right? I am asking you to draw the Hasse diagram for the power set A. So what is power set elements? I do have singleton A, I have singleton B, I have singleton C, I have AB, I have BC, I have AC, and also I have ABC as the superset and also null set. So therefore there will be 8 sets here, for which I will have to draw the Hasse diagram. So Hasse diagram, let us see. So the least element I will have here, right? The maximum element I will have here ABC, and in between I can have, that is A, singleton B, singleton C, and then here AB, then AC, then BC I will have. Now see here, this is a subset of this, fine. So no need to have an arrow mark. Again, A is a subset of AB, A is a subset of AC, B is a subset of B, and B is a subset of BC. Now C is a subset of AC as well as C is a subset of BC. Then again these 3 are subsets of ABC. So this is how one will be drawing the Hasse diagram. Alright. So this is all about the Hasse diagram. Next is, even if you want to find out the lower bound and upper bound for any lattice, alright, I'll just give you, write down the divisors of 30. So D represents the divisors of 30. What are all the divisors of 30? We can have it. So 1 is a divisor of 30, 2 is a divisor of 30, 3 is a divisor of 30, and 4 we don't have. 5 is a divisor of 30, 6 is a divisor of 30, then 10 is a divisor of 30, 15 is a divisor of 30, and 30 is again a divisor of 30. Draw the Hasse diagram for this. So we will have a least element here and we will have the topmost element. Alright. So then I can have 2, 3, 5. Then I can have here 6, 10, 15. Now see here, 1 divides 2, 1 divides 3, 1 divides 5. 2 divides 6, 2 divides 6, 10. 3 divides 6, 3 divides 15. 5 divides 10, 5 divides 15, right? 6 divides 30, 10 divides 30 and 15 divides 30. So, this is the Hasse diagram for the divisors of 30. And next is, if I am asking you to find out, right, if I am asking you to find out the lower bounds of 10 and 15, lower bounds of 10 and 15. What are the lower bounds of 10 and 15? We have 10, 15, the common thing we should have. The 5 divides 10, 5 divides, but then 3 only divides this. So, the lower bounds are 1 and 5. The lower bounds of 10 and 15 are 1 and 5. So, then how do we find out the greatest lower bound of 10 and 15? So, greatest lower bound is nothing else but already I would have got the lower bounds, of which I will have to find out the greatest value. So, 5 will be the greatest lower bound of 10 and 15. And next is what is the upper bound of, right? What is the upper bound of 2 and 5, right? So, the upper bounds of 2 and 5, 2 divides 6, 2 divides 10. 5 divides 10, 5 divides 15. So, the common is 2 divides 10 as well as 2 and 5 divides 30, right? The upper bounds are this. What is the least upper bound of 2 and 5? So, least upper bound, among which I had to find out the least. So, this is my least. So, that is how we will be finding out the lower bound, greatest lower bound, upper bound and least upper bound of any Hasse diagram, right. So, whatever may be the given relation, and if we are supposed to find or draw the Hasse diagram, this is how one have to do it. Next, we have distributive lattice. So, now we know what is a lattice. Lattice means each and every pair of elements should have a least upper bound and the greatest lower bound. So, distributive lattice na, any lattice which satisfies the distributive property is said to be a distributive lattice, right? Any lattice. So, distributive lattice, any lattice which satisfies the property of distributive. That is, what is the property we have? A or B and C is equal to A or B and B, A or C. And next is A and B or C will be equal to A and B or A and C. So, this is said to any lattice which satisfies this distributive property is said to be a distributive lattice, right. And next is bounded lattice. What is all about the bounded lattice? So, bounded means it should have a boundary, right. So, now the lattice we will write it to be as L, R, and in general. Why do I represent the lattice as L, R, and in the sense L stands for lattice, and if it has to be a lattice, it should, every pair of elements should have a least upper bound as well as the greatest lower bound, and R should be there. So, that is why we are writing here the operators R and along with the set L. So, then it is said to be a lattice. So, then after knowing what is a lattice, the notation of lattice, how do we define a bounded lattice? So, bounded lattice means any lattice which is within the boundary, which means that I have L, R and 0, 1. So, the minimum should be 0 and the maximum should be 1. If that is so, then it is said to be a bounded lattice. See here, in a bounded lattice L and R 0, 1, an element B belongs to L is called a complement of an element A belongs to L if I have A and B equal to 0 or A or B equal to 1. So, suppose if there is an element B belongs to L, right, and this element B will be called as a complement of A in the lattice L if it satisfies the condition as A and B equal to 0, A or B equal to 1. Then I will call A to be a complement of B. So if that way I say it, then the lattice is said to be a bounded lattice. And next, coming on to the complemented lattice. So complemented lattice is if every element of lattice L has at least one complement, right? So I may have many elements of which if I have only one complement, then it is said to be a complemented lattice. Say for example, I have the elements as A, B, C belonging to the lattice L. So now when do I say that lattice to be as a complemented lattice? In the sense, at least any one element of that should have a complement. So I have totally 3 elements. If at least this A has a complement in L, then it is said to be a complemented lattice. Any one, it is not necessary that for all the elements we should have the complement. At least for any one we have a complement, then it is said to be a complemented lattice. And next, coming on to the sublattice. So sublattice means, first of all, we will have to say like I'll denote the set to be as sublattice as S, right? And lattice, see, suppose for example we have a lattice, right? We have a lattice as like this element, right? A, B, C, D, E, F, C, right? So this is a lattice. When do I call this lattice to be a sublattice? Is that the subsets of this lattice should have a least upper bound as well as the greatest lower bound, right? So the subsets, now I can have this A, B, C, D, right? A, B, C, D is a subset of this. So this becomes a sublattice. How do I say this to be a sublattice here? Is that B and CK I have A, B or CK I have D, right? So this is a sublattice. So whatever subset I have of the lattice, for that subset I should have a least upper bound and the greatest lower bound. Say for example, now in this point, like I'll have E. So this is not a sublattice. This is not a sublattice. Why it is not a sublattice is that, see here, for D and E, that is D and E, I don't have the lower bound, or D, this guy I don't have it. So that is why this is not a sublattice. Understood now? Sublattice, now each and every pair of that subset should also have a least upper bound as well as the greatest lower bound. So that is called as the sublattice. So now we will see a problem of this. Show that both the least upper bound and the greatest lower bound of any elements in a partially ordered set are unique. So how do I prove this? Least upper bound, greatest lower bound of any elements in the given partially ordered set should be unique. So even if I have 2 or more number as least upper bound or greatest lower bound of any element, I should be able to prove it has only one least upper bound and one greatest lower bound. It may have many upper bounds and it may have many lower bounds, of which I should have only one least and one greatest. So let us see how do we get the proof of this. So now let me take the lattice L comma less than or equal to be a lattice, right? And then A and B are elements in that lattice L. Now how do I say that I will have, that is, only one least upper bound and only one greatest lower bound of this lattice or the partially ordered set? So now for it to be a lattice, each and every pair will have a least upper bound, which means that for it to be a lattice, I have least upper bound, that is A or B, and A and B will be there in L, right? A or B and A and B will be there in L. So now let me suppose that, first let me case 1, I will show it for LUB as unique. So LUB as unique na upper bound. So what is this? A or B is the least upper bound, and that has to be a unique, and I will have to prove it. Let me check out that. That is, upper bounds I may have to be as A is less than or equal to U1, B is less than or equal to U2. See here, I have two elements and those two elements are less than or equal to U1 and U2, which means that from here I can say that U1 and U2 are upper bounds in L, right? Upper bounds in L for A and B. So, if U1 and U2 are upper bounds, definitely I under the assumption that see, for example, I can say that among these two upper bounds, if suppose if my U1, right, if my U1 is less than or equal to U2, right, which means that comparatively my U1 is less than or equal to U2 na, then I can say that my U1 will be the least upper bound, right. So, which means that my U2 will be less than or equal to U1. So, from these two I can write it to be as U1 is equal to U2. See here, I have got two upper bounds, and of these two upper bounds I have said that both are one and the same. So, therefore, the least upper bound is unique. And next, case 2, for greatest lower bound to be unique. How do I say that? That is, let A comma B belongs to the lattice L. Lower bound, right? So, lower bound na I have A and B, right? So, which means that let L1 is less than or equal to A and L2 is less than or equal to B. So, therefore, L1 and L2 are lower bounds of A and B. Lower bounds of A and B. Now, under the assumption that, right, of these two, suppose in case if my L1 is less than or equal to L2, then my greatest lower bound will be this. On the other hand, if I have L2 to be the least, I will have L2 is less than or equal to this. So, from these two, I will have L2 is equal to L1. So, therefore, GLB is unique here. And next, let L comma less than or equal to be a lattice and A comma B belongs to L. If A is less than or equal to B, then show that A or B is equal to B and A and B is equal to A, right. So, how do we give the proof of this? What is given? Given is a lattice, right. Given is L comma less than or equal to is a lattice, and then it says that A and B are two elements in L, and also it is given that A is less than or equal to B. So, with this we are supposed to prove A or B equal to B. So, how do we prove this? Now, this I can mark it to be as 1. This again I am telling you, this less than or equal to does not mean that it is exactly less than or equal to, it is some relation, we are just comparing it, unless otherwise it is specified. So, I can also say that the element can be compared to itself, B is less than or equal to B, right. So, now I take R on 1 and 2. If I take R on 1 and 2, I will have A or B is less than or equal to, right, A or B is less than or equal to B or B, and A or B is less than or equal to B. So, let this be my third inequality. And next is, but as far as set theory is considered, please have a quick review on the set theory. I will have two sets as A and B here. So, my A union B will be the entire portion, right. A union B will be the entire portion. So, will I not be able to say that my B will be a subset of A union B in this case? Yes. Likewise, here I can say that my B will be less than or equal to A or B. Let it be 4, right. Obviously, this is true. Now from 3 and 4, right, from 3 and 4 we get, right, A or B equal to B. So that is what our first case we have proved it. The next case is given this to prove A and B is equal to A. So what is given? Given is A less than or equal to B. Have it as equation 1, right? And now when I go to the set theory, I can compare any element to itself. I will have A is less than or equal to A, mark it as 2. Now take and on both sides of 1 and 2. So I will have A and A is less than or equal to A and B, or A is less than or equal to A and B, mark this to be as 3. Now again go to the set theory. So in the set theory, you just find out what is your A intersection B. This is A, this is B. This is your A intersection B. And A intersection B, is it not a subset of A? Fine. So that way if I compare it, I can say that this is less than or equal to A. So from 3 and 4, this is obvious. Obviously. So now from 3 and 4, I get A and B is equal to A. That is what we need to prove, right? So only one thing we will have to keep in mind everywhere here is that all the basic definitions we should be very much thorough of it, and we should also have been recalling the property every now and then. Next we have, let L comma less than or equal to be a lattice for any 3 elements A, B, C which belongs to L. If B is less than or equal to C, this should imply A and B less than or equal to A and C, and again B less than or equal to C, we should imply A or B less than or equal to A or C. So let us see that here. Now what is given? With the given thing we will have to go. Given is L comma less than or equal to is a lattice. Then A, B, C, also given that A, B, C are elements in L, and also it is given that B is less than or equal to C. That is given. You mark this to be as equation number 1. With this we are supposed to prove this inequality. And now what does that A and B imply? Right? A and B, what does it imply? So A and B is the GLB of A and B. And also it will say that A and B is lower bound of A and B. So this will imply that A and B is lower bound. So which means that A and B will be less than or equal to A, as well as A and B will be less than or equal to B. This is lower bound. Since because it is lower bound, we will have this. And now what is given? B is less than or equal to C is given. So using that, I can write this to be as A is less than or equal to C, right? See, I have this to be as 2, this to be as 3, right? So now taking and of 2 and 3, and of 2 and 3, what do I get? A and B and A and B will be less than or equal to A and C. So this will imply A and B is less than or equal to A and C. That is what this proof. I have got this. And next case, to prove this one, I will take, what is my ARC? ARC is least upper bound of A and B. That is, this will imply ARC is upper bound of A and B. So upper bound in the sense, ARC will be greater than, right? ARC will be greater than or equal to A, as well as ARC will be greater than or equal to, am I right? C. And now what is given? Or I can say that this is same as A less than or equal to ARC and C is less than or equal to ARC. And now what is given? Given is B is less than or equal to C. which means that from this I can have, right, B is less than or equal to A or C. Here I have this to be as 4, I can have this to be as 5. And now take, right, take OR of 4 and 5. What do I get? Left hand side like A or B I will have is less than or equal to A or C or A or C. So which means that A or B is less than or equal to A or C. So that is what the second proof also, right. And next is prove that the lattice given is not distributive. Prove that the given lattice is not a distributive lattice. How do we prove that it is not a distributive lattice? Any lattice which satisfies the distributive property is said to be a distributive lattice. Let us check out that property. If that property does not hold here, then the given lattice is not a distributive lattice. Alright. So now here, right. So 0 is less than or equal to A, 0 is less than or equal to B, less than in the sense they are related. 0 is related to C. And again A is related to 1, B is related to 1, C is related to 1. But then A, B, they are not related, right. A, B not related, B, C not related, A, C not related. So now take distributive lattice A or B and C is A or B and A or C. Take the left hand side, right. So now here they are not. So what is given here? Again A and B is 0. Okay, fine. We will have the left hand side A or B and C. So now this is equal to A or B and C. So B and C, it is 0, right. A or this is A. Let me see this here. Right hand side I will take here. That is A or B and A or C. So this is equal to A or B is 1, right. A or C is 1, which is 1. But then A is not, this is not equal to LHS is not equal to RHS. Therefore, it is not distributive. Right. So this is how we will have to check it out. And we will see now here Boolean algebra. So what is a Boolean algebra? It is a lattice which contains a least element and the greatest element, and that should be both complemented and distributive, right. What is a Boolean algebra? It should be a lattice. So lattice na definitely it will have a least element and the greatest element, and also moreover that must be both complemented and distributive. So then it is said to be a Boolean algebra. So next is chain. Any lattice is said to be chain if it satisfies two conditions. That is, if I have 3 elements in the lattice L, first case says that A less than or equal to B less than or equal to C, and the next case says that A greater than or equal to B greater than or equal to C. So this is called as a chain. Chain, it has to be related. Show that every chain is a distributive lattice. So distributive na, I will have A or B and C is equal to A or B and A or C, or else A and B or C, I will have it to be as A and B or A and C. So now I will have to prove my chain is distributive. Case 1, I will have the case to be as A less than or equal to B less than or equal to C. So now which means that A I will have here B and then C. A, B, C. I am comparing. So A is least of these two, right. So now let me take my LHS of 1. In a similar manner, we will have to do it for the next one, A or B and C. So what is B and C? Lower bound of B and C is B only, A or B. What is upper bound of A or B? It is B. Now take the right hand side. So your right hand side is A or B and A or C, which is equal to A or B. What is the upper bound of A and B? It is B. What is A or C upper bound? It is C. What is B and C lower bound? It is B. see here LHS is equal to RHS. Again, for this two similarly it can be done for A and B or C, that is equal to A and B or A and C. And next case 2. Case 2, what it says, A is greater than or equal to. So, I will have C here, B, A, right. So, A greater than or equal to B greater than or equal to C. Now, I will take the left hand side part, which is A or B and C, which is A or what is lower bound of B and C, that is C. What is upper bound of A and C, that is A. Next is RHS. RHS part is A or B and A or C. So, that is A or B. What is A or B? Upper bound of A and B is A. A or C upper bound is what? A. That is equal to A. So, therefore, LHS equal to RHS, and similarly we can also have A for A and B or C is equal to A and B or A and C.